The Great Pyramid of Giza is an extreme mathematical boundary condition. It is a structure defined by 2.58 million cubic meters of volume and roughly 6 million tons of mass. Pharaoh Khufu's reign set an absolute deadline on this mass, 20 years to complete the entire structure. Dividing 2.3 million blocks by a 20-year, 10-hour workday yields a restrictive bottleneck. To finish on time, they had to quarry, transport, and position one block exactly every 120 seconds, continuously. A 2-minute cadence leaves zero margin for error. A single choke point anywhere on the construction site would halt the entire project. Executing this requires an architecture of massive parallel operations. This 120-second cadence necessitates an industrial-scale logistics plan, posing a severe challenge to any construction model that relies on a single linear pathway. For centuries, the debate over the pyramid's construction has been trapped by searching for a single method. This infographic outlines 5 prominent historical hypotheses: external linear ramps, internal spiral ramps, wet sand sledge transport, modular staging, and multi-method integration. We are going to subject each of these theories to a mathematical stress test. We will measure them against basic physics, specifically friction coefficients, material volume limits, and narrowing pyramid geometry. Surviving this math requires abandoning the idea of a single solution. The numbers suggest a complex, phase-dependent hybrid architecture. Any viable theory has to operate strictly within the technological baseline available to Fourth-Dynasty engineers. Metallurgical analysis proves their tools were forged from arsenical copper. When combined with a quartz sand abrasive, this alloy possesses the necessary tensile strength to cut limestone. Moving those cut blocks horizontally relied on heavy wooden sledges pulled across the desert. Dry sand piles up in front of a sledge, creating immense drag. But by adding a specific percentage of water, liquid capillary bridges form between the individual grains, stiffening the path. The lower panel shows the wet sand technique drops the friction coefficient from 0.6 to 0.25, a 55% reduction. Applied to mass equations, the pull force for a 2.5-ton block drops to 6,131 newtons, manageable for the 41-person team. Optimizing horizontal friction solves the problem of ground transport from the quarries, but vertical lifting remains a separate challenge of physics. One common theory is the use of a single, massive external linear ramp. To manually haul a 2.5-ton block up an incline, the slope's gradient cannot exceed 8%. Calculating the dimensions to reach the 146-meter apex at an 8% gradient, the ramp must extend 1.8 kilometers into the desert. This presents a volumetric flaw. Its total volume hits 4 million cubic meters, exceeding the pyramid itself by 60%. To fix this volume issue, an alternative theory proposes an external spiral ramp. Wrapping the incline around the structure saves material volume, taking advantage of the wide base. However, this creates a geometric failure. At the 100-meter mark, the side length shrinks to just 73 meters, bottlenecking the 120-second placement rate. Additionally, this spiral covers the structure's corners, obstructing the necessary lines of sight and Mercator's stellar observations required for sub-arc minute alignment. The mathematics show external ramps are strictly viable only for the wide lower portions of the structure. Reaching the apex forced a change in methodology. This brings us to the Grand Gallery, a 47-meter internal void, inclined at 26.5 degrees. These deep, semicircular grooves, labeled here as alpha, are cut directly into the antechamber wainscot. Engineering analysis suggests these grooves were structural rests for heavy wooden winch rollers. This diagram maps out how those antechamber rollers acted as a pulley block, connected by heavy ropes to a counterweight inside the Grand Gallery. Following the force vector shown, an 11-ton granite sled descending the 26.5-degree slope creates a 2-to-1 mechanical advantage. Harnessing gravity in this way allows a descending weight to hoist standard 2.5-ton blocks up the internal vertical shafts. The Grand Gallery acted as a calibrated industrial engine, purpose-built to overcome the geometric limits of external ramps. The builders optimized their construction by changing techniques as the geometry shifted. This diagram visualizes that hybrid model. Phase 1, in blue, uses external linear ramps to build the bottom 43 meters. Because the base is wide, this completes 65% of the total volume efficiently. Phase 2, marked in orange, shifts operations inward. From 43 to 100 meters, builders used internal spiral ramps and the Grand Gallery counterweight engine, keeping corners clear for surveying. Finally, Phase 3 in green finished the tightly constrained volume near the apex using localized levering. This adaptive three-phase pipeline is the only model that resolves the physical and geometrical contradictions found in single-method theories. To confirm this approach was humanly possible, we must establish the total energy budget. The effort to list 6 million tons to a centroid height of 36.6 meters equals 2.15 trillion joules of gravitational potential energy. Dividing that requirement by a sustained human output of 75 watts per person over 6,000 working days provides a final metric. The vertical lifting task required an active force of only 166 continuous workers. The Great Pyramid stands as a monument to phase-dependent systems engineering, achieving a 6 million ton scale through modular project management.